Next slide.
Yep.
And I just want to remind us before we get started about this definition of resilience that we've been using throughout the program and the webinar series. So again, we're looking at the capacity of an individual or a community exposed to hazards to adapt, and adapting by resisting or changing so they can reach and maintain an acceptable level of function and structure. So this really is looking at that ability to kind of bounce back and to recover after a disaster. And it's usually that recovery and sort of that ability to bounce back and to adapt, often happens based on how we organize and kind of learn from our past experiences. So we've already learned a lot in this series about ways that you at home can adapt and be more resilient, and also how your community can be more resilient. And Eben today will be talking quite a bit about that community portion, as well as some of that individual resilience.
Thanks so much, Holly. So I wanted to start out kind of building off of this great series that you all have put together, really talking kind of what are we talking about in the scope of community resilience and individual resilience here. When we think about community resilience as it pertains to gray infrastructure and stormwater management, we think about sort of the roads and bridges that help us be able to move around in our communities. We think about functioning and drainage of our stormwater system so that it's able to move water out so that we don't have flooding. But there's also sort of the individual resilience as well. And this is really understanding sort of from your own property perspective, how water flows onto or off of your property, and also how to protect sort of your property from flooding whenever we do have sort of large rain events. So to start off kind of going into this whole aspect of gray infrastructure, really thinking about sort of the basics here, and some of you may be kind of familiar with some of these concepts, but looking at sort of what happens, when we change an area from basically undeveloped, maybe it's forested, maybe it's an ag field, and then making that into an urbanized or developed area. There's several things that really kind of occur. And just to point out here, the graph that I'm showing here, the blue bars represent the rainfall that happens during a sort of what we call a center weighted storm, but basically it gets more and more intense and then tapers off, like many of the storms that we end up having. And then the lines that are shown there for undeveloped and urbanized are the rate and sort of the amount of runoff that occur. So the shift from the undeveloped to urbanized is what we kind of want to look at here. And what you should see, hopefully, is a couple of things. Number one, there's a greater total runoff volume from the urbanized compared to the undeveloped response to that rainfall. There's also a shorter time to the peaks. So if you look at where the undeveloped and urbanized peaks kind of happen, the urbanized peak happens much quicker after the peak rainfall than the undeveloped. And that's due to the stormwater infrastructure optimizing the conveyance and movement of water from where it becomes runoff to the downstream area. And so this is where we get the term sort of flashier or flash floods that occur. And then there's an overall higher peak runoff rate. And so that can introduce risks of flooding downstream, particularly if many areas are contributing at once. And so I mentioned before that, a lot of our drainage network is essentially about getting water from where it becomes runoff downstream and offsite. And we have really kind of taken that approach really up until kind of the 70s and 80s, that it was really about just getting that water offsite as quickly as possible so that we're not flooding ourselves and our own property. But municipalities built these storm sewer systems to drain usually to the nearest creek, river, or wetland or pond so that we could not have flooding on our property. And you can see sort of the different elements in the urban area. We have scuppers on the side of buildings. We have storm drains along the side of streets. And then we have the pipes where they discharge into those downstream waters. So Along around the 70s and 80s, we realized that all of that water contributing downstream as quickly as possible and flooding out people downstream is maybe not the best or most responsible way to manage stormwater runoff. And so uh, along came an approach called peak control. And this was essentially the idea that instead of just allowing all that runoff to go, that increased amount of runoff to go off-site and downstream, we should capture and control the release of that stormwater runoff so that it is comparable in some ways to what happened before the area was developed. So essentially, with detention, we basically have these ponds where runoff is directed, fills up a pond, and then slowly discharges it downstream. So it reduces the peak rate. It's the same amount of volume, essentially, that goes downstream, but it also prevents downstream erosion or reduces the likelihood of that. And so this sort of yellow dashed line indicates sort of that pre-developed runoff peak. And so what we've done with the modified or peak controlled runoff is sort of stretch that out. And so you can see that sort of yellow, orangish yellow at the bottom that's just hugging underneath that yellow dotted line. The water quantity is not the only issue with stormwater runoff that we have to deal with. I'm sure many of you are aware of the impacts of water quality from stormwater runoff. A lot of our developed areas, like our roadways, contribute metals, polyaromatic hydrocarbons. Our parking lots and other impervious surfaces can contribute organic debris, sediments, and nitrogen that gets deposited just from the atmosphere. Then we also have, management of landscapes. If we're not applying nutrients properly, then those can be sources into our stormwater system and move downstream. And as cute as this puppy is, it's not mine. My dog's nowhere near as cute as this. They are essentially walking, barking point sources of pollution. And so it's important to pick up after our pets to prevent the introduction of nutrients as well as pathogens into the flow path of our water bodies, or basically the flow path that contributes to our water bodies. And if we look at the impacts of stormwater runoff in these chemicals or pollutants in stormwater runoff and the overall quantity of runoff that's coming off the landscape, we can have some pretty significant impacts. Everything from algal blooms that contribute to fish kills to downstream flooding that is still a significant occurrence in many areas. And this channel in the bottom left is an example of erosion where it was an old ag ditch. The area got developed. All the stormwater went into this small ditch that was probably initially only maybe a foot deep. And this is my friend who's about 6'5", and it's about 20 feet deep and about 6 feet across. So the erosion that can occur from unmanaged stormwater runoff. So the impacts are multifold. And so we have to design and address these multiple facets or multiple impacts of stormwater runoff with our stormwater systems. So the conventional approach that many of you have probably seen, and the most common one here in Florida and in many areas around the United States as well, is to collect the runoff from a developed area through stormwater inlets that then connect to a stormwater pipe or stormwater collection system that then goes into a stormwater pond. And that pond serves multiple functions. The first being that it provides flood control. This is where water can flow quickly into the pond, stage up, and then it slowly gets released out after the storm is kind of dissipating or dying or over. It also reduces the flow rate and reduces the risk of that erosion. And there's also sort of a water quality volume where there is credit for the treatment and removal of nutrients. One of the big aspects, though, of water quality volume is that the intentions behind this were good to assign water quality volume. However, in Florida, we found that these stormwater ponds are not necessarily providing the amount of treatment that they are credited with. So there's a couple graphs here. Essentially, I want to walk through sort of the upper two graphs, kind of show what the concentration of nitrogen and phosphorus, two key nutrients that contribute to algal blooms, what they are in the inflow versus the outflow. And so we see with nitrogen, it goes from a median of 1.65 down to 1.2, which is about a 25% reduction. Whereas with phosphorus, we reduce it by about 2/3 from 0.3 down to about 0.1. Compare that to their credited, historically, they were credited with about 80% nitrogen and phosphorus removal. But what we really see is that they're much less than that. Below are two graphs that essentially show that over that ponds holding water for long periods of time, the total removal efficiency, not just the concentrations, the total removal efficiency from ponds for nitrogen never even gets close to that 80%. It really kind of caps at around 45% nitrogen removal, whereas phosphorus can get up to about 80 if we have a detention time of about 200 days. Now, there's a reason that phosphorus is better removed than nitrogen. One of the aspects is that stormwater ponds in this water quality credit were based on stormwater ponds being able to remove sediments. So if you think about sort of water that's moving and has sort of sand or silts or other particles in it, it's moving quickly. It can carry a lot of sediments with it because of that momentum. When it then goes into a pond, the velocity stops and those particles then can settle out pretty quickly from the suspension. And so you can get pretty effective removal of sediments. Well, phosphorus, a lot of it is bound to sediment particles. And that's why we have sort of some benefits, but more benefits for phosphorus removal than nitrogen. Nitrogen's a different animal, though. Nitrogen is oftentimes not as associated with those sediment particles, and it's mostly in a dissolved fraction. And so what we see is that there is a certain fraction that does settle out when the stormwater comes into a pond, and we get about half of that nitrogen removed. But then the other half basically stays in suspension, and we don't get that removed at all. And if we take a look at sort of the relationship between urban areas and impaired water bodies, on the left is a map of basically our urban areas in northeastern Florida. And on the right, same area with water bodies or basins where the water bodies are not meeting their water quality standards. We can see that there's a lot of overlap between areas that are urbanized and the areas that are not meeting their water quality requirements or water quality standards. And this kind of has created a stormwater legacy, right? Where we put in this stormwater infrastructure, it's credited to remove or treat our water quality. And so that's kind of set in stone. It's hard to go back and correct or fix that, particularly when there's limited land in these areas that have been developed. There's limited areas to work with to improve that. And this is where low impact development, green stormwater infrastructure kind of come into play. And if you're not familiar with these terms, I want to give you sort of some basic definitions to kind of think about them. If you have heard of them before, you might think of them as the same thing. But I think these definitions really kind of distinguish them from each other in how they apply to different phases of the development process. So low impact development is a comprehensive site planning and design strategy for maintaining pre-development hydrologic regime. So basically trying to have the same response or similar response to rain events for a site before and after it is developed. And this also focuses on mitigating the pollutants from land development using distributed structural and non-structural design techniques. But the goals here are to avoid and minimize the runoff being produced from the site. So a lot of this is looking at how do we minimize the impervious, and then how do we reduce or infiltrate any runoff that might come from those impervious areas very close by, just by disconnecting impervious area. And then green stormwater infrastructure are the actual structural and non-structural retention and detention measures that are designed to infiltrate, evaporate, detain, filter, treat stormwater runoff closer to the source. And the goal here is basically to mitigate the runoff that is generated and could not be avoided or minimized. So first is LID and the site planning and layout. And then GSI is basically coming in and addressing or mitigating what could not be avoided or minimized. So together we say these are LID and GSI. I really like this figure. It's from a manual that, from the University of Arkansas, and I think Carrie can put a link to where you can find some examples of or example of this manual in the chat. But one, I think it provides a really great kind of comparison between our philosophies or kind of our approaches, how they've evolved from initially being sort of this hard engineering pipe and pond and just relying on concrete structures and then detention basins and then discharging and sort of that approach to more of a holistic integrated LID GSI approach where we really try to think about how do we integrate natural processes into the built environment and providing filtration, infiltration, and treatment of stormwater along its flow path. I really like this is the manual I was talking about. I really like this. It has it's just such a great graphical illustration. I'm a stormwater nerd, and my family is not very interested in the things that I find really exciting. But this is a manual that I think of it as the coffee table book of stormwater management. It's just so graphical. It provides such a visual representation of a lot of the things that we're dealing with. And if you go to the link that's here or that Carrie provides, you can see some more excerpts of it. It's really fascinating. They do a great job of kind of laying out some of these concepts and really providing an easy way to understand these. Really even breaking down a lot of these more complex processes of how do pollutants come in, what pollutants are coming in, inputs and outputs, how do plants approach that and help to filter it. And then it brings it all together into some of these examples of how these processes can be integrated into the modern built environment. And so I kind of alluded to this a little earlier, but this kind of graphic shows the really kind of the transition from site planning to mitigating here, where we talk about, at the front end, the LID takes place with avoiding runoff. So what this means is essentially identifying the areas on the site that are valuable natural infrastructure to preserve those so that we can retain those hydrologic features and retain that large scale hydrologic performance. Now, with development, there is some areas that do have to be converted to impervious surfaces for different types of structures and so forth. But with LID, we look to minimize the generation of that runoff, limiting the footprint, disconnecting impervious surfaces. So you don't have a rooftop flow, draining to a gutter that goes onto a driveway, into a street, and then into the storm drain. It can run off into the landscape, whether that's turf or some other type of natural area, so that it is infiltrating and being treated on site rather than just contributing downstream. And then again, anything that's not able to be addressed or mitigated, that is addressed by green stormwater infrastructure, by implementing these source controls and really looking at how do we integrate these natural processes to treat stormwater runoff. So going in depth a little bit more with this whole avoid aspect and the planning, it really starts at the planning stage. To go in a little bit more detail here, number one is preserving those open spaces and natural areas as much as possible. With development, you're not going to be able to preserve it all, but there is value to preserving as much of that as possible. Maximizing the retention of native forests and preserving those permeable native soils that really promote infiltration and filtration of that water as it goes into the ground. You also want to incorporate sort of those natural flow paths and protecting those, the topographic features that essentially slow down water as it moves across a landscape so that it's not just moving from one point to the next as efficiently as possible. Slowing it down also allows for it to be filtered and infiltrate into the ground. And then again, we're trying to reach this aspect of maintaining that pre-development hydrology, mitigating those peak discharges and volumes, and so forth. We look at sort of an example of what this might look like between a traditional or a conventional and a low impact development uh, site. This is what we might look at here. Notice on the left, traditional or conventional, we've got every lot is essentially maximized and cleared. You've got pretty wide streets, cul-de-sacs, and we've got a few stormwater ponds or basins that are scattered around the edge of the property. If we look on the right, though, we have the same number of lots. They're a little bit smaller in area for each one, but there's conservation space on the left side. We have bioswales that move in between the homes and capture and infiltrate and treat stormwater runoff. This before it gets downstream to really our flood control practice. We've utilized sort of the open space, kind of the same area on both of those at the bottom of the layouts. But they've also limited the impervious area here by narrowing the streets. And they've been able to capture or basically preserve this conservation area on the left by clustering the homes, putting them a little bit closer together and compacting that development so that you preserve more of this natural area on the left side there. Another example of this is a site that was designed for a neighborhood called Restoration. And this was in a plan for East Central Florida. They started out initially with the plan on the left, and there was a lot of wetlands and forest that was going to be impacted. And then they came back and wanted to, were encouraged to try to take a more low impact development approach and limit the amount of impacts on area to the west side or the left side of the map here. And they were able to basically cluster all of the development, same amount of square footage and area in the right-hand side here, and basically limiting the amount of imperviousness, reducing drive times, and also increasing the building vertically, and reducing the amount of areas that needed to be that were urban landscape that needed to be managed on a regular basis. So as we go into phase two, so the second stage is now minimizing. How do we basically make the project fit the site? A lot of times we see that we want the site to fit the project. We have a project in mind and we force it onto the site. It's where you see kind of a sites that are cleared and mass grading done where they recontour the entire site. We'd like to move away from that and really make use of what the existing topography of the site is and what those features are. So this involves minimizing and disconnecting those impervious surfaces, trying to control runoff at the source, using those small distributed hydrologic controls. These are green stormwater infrastructure I'll talk about more in detail in a minute. Looking at more redundant runoff controls, so not just relying on one type of practice, but multiple ones. Really thinking about the whole water cycle, so maximizing infiltration, evapotranspiration, the filtration and storage of stormwater throughout the site. We also want to reduce our over-reliance on traditional stormwater conveyance and pond technologies. We want to slow the water down by creating a rough hydrologic landscape so that water doesn't move super quickly. That rough hydrologic landscape allows water to infiltrate and be filtered. And then employing sort of natural processes for water quality improvement. And then building off of that, integrating those stormwater controls into the development design as an amenity. A lot of times these areas provide a lot of value, whether it's shade trees from natural areas that are preserved or recreational areas for these spaces. And then we're developing reliable maintenance programs that ensure that these practices continue to work and continue to provide their services. So when we think about limiting imperviousness, this is really about how do we reduce the amount of impervious cover. Some of that is looking at narrower streets and using swales. So narrower streets automatically kind of slows the velocity that people are willing to drive, because if you've got a smaller space, you don't want to be flying down and having somebody come within a couple feet of your car. You naturally want to go a little bit slower. We can reduce the length of driveways, particularly if we're clustering homes together. It doesn't seem like it's an odd thing to have sort of shorter driveways when it's like we're in a tighter community here. And then there's the aspect of just reducing the size of lots. And instead of just only going with single story, we can go to multi-story to reduce the housing footprint. When we think about this disconnecting imperviousness, this is really about how do we put spaces adjacent to where stormwater runoff is generated, like in a parking lot or on a roadway, where that water can run off, build up, infiltrate, and potentially, if there's enough water, maybe then it discharges to somewhere else. But this allows for pre-treatment of that water that is coming off of those roadways. And I'll talk about this a little bit later on, but there's an aspect of what's called the first flush, that first little amount of water that comes from these afternoon thunderstorms. The most of pollutants that come off of our impervious surfaces are washed off in that first amount of rainfall. Usually we say it's about the first inch. So if we can capture and infiltrate that first inch, we can really try to reduce the amount of water quality pollutants that are going downstream. Other opportunities to disconnect imperviousness is to make the traffic islands, instead of making them mounds, making them depressed so that they can receive sort of runoff from the adjacent parking areas and roadways. This allows that water to build up in these sort of open areas of the parking lot and then infiltrate into the ground. And then moving on to phase 3. So once we've basically tried to mitigate, avoid and minimize the runoff from the site plan as much as possible, then we look for where we can incorporate green stormwater infrastructure into the landscape to mitigate the runoff that could not be avoided or minimized. And there's a lot of different names up here. I'm going to go over these in a little bit more detail, but things like, if you've heard of green roofs, pervious paving, rain gardens or bioretention, wetlands, stormwater ponds are a type of green infrastructure. It provides its own types of benefits, mostly on flood control, okay? But it is a type of green infrastructure. We also have things such as cisterns and rainwater harvesting, tree filters or tree wells, and other types of practices. So what does this look like in the conventional, what is the conventional kind of orientation or configuration look like within an LID GSI approach? Well, we still have the issue when we have development of having to mitigate or control for flood. That flood control is not going away, right? We're still going to have to protect property and the public from the risk of flooding when we add imperviousness to an area. Instead of, though, that water essentially going off of the individual lots and then directly into the storm drain, we look to capture that water, infiltrate it, treat it before it then either overflows or maybe it's being filtered as it moves along. That water quality aspect is happening upstream of it entering the stormwater collection system. And so this looks like having rain gardens and cisterns and other smaller practices within the urban landscape, right? So instead of the stormwater pond being relied upon for flood control and water quality, it's really just being relied on for flood control, and our water quality is really being addressed in the landscape. So let's look at some of these practices, and some of these you may be surprised to be somewhat familiar with. So cisterns, these are an extremely old technology. They've been used for thousands of years. In many places, they were being used for water supply. And here they can kind of offset some of our water uses, but really as a way of capturing runoff and not letting it discharge off site. So these cisterns can either be above ground or buried below ground. And they essentially fill up during rainstorms. And usually it's getting direct runoff from a rooftop. And then the recovery of that volume is done through non-potable, you're not consuming this water, but it's used through irrigation of the landscape, maybe vehicle washing or flushing of toilets. Now, if you have a rain barrel or you've seen one, those are essentially just small cisterns that are scaled down to maybe an individual roof downspout. The key here with the operation of cisterns, though, is that it only can reduce the amount of runoff that it has storage available for. So it's important that in between rain events, it's able to draw down or recover that volume so that it has enough capacity when the next rainstorm happens. So it's important to make sure you're using that water on a regular basis. Stormwater planters are another type of technology. These basically reduce runoff and they treat the runoff as well. I'll talk a little bit more in detail about what bioretention is, but this is sort of bioretention in a box. A lot of times these are right up against between the building and the sidewalk rather than between the sidewalk and the street. So it's almost like integrated into the building infrastructure in some ways. But it can definitely take sort of that roof downspout, the water that comes down the downspout. And these basically recover the volume through vegetation evapotranspirating, or basically taking up that water and using it as it fills up that area. And it's very effective for removing suspended solids that might clog other things downstream. It can, if you weren't using this as a stormwater practice, this might just look like pretty landscaping. So these can be fairly aesthetically pleasing. We're just, with some additional thought into the design, incorporating this function of treatment and runoff reduction. So it can really provide some of those functions. Permeable pavements. These are one of my favorite practices. When I got started in this industry or this field, oh gosh, maybe 20 years ago, I did some of my first research on this. And permeable pavements are really interesting because unlike the conventional types of pavements, it allows water to drain through this material. So you have porous asphalt and porous concrete and pervious pavers or concrete pavers. And while the surface is a little bit different, the composition or the profile is pretty similar across those. You essentially have this pervious surface that allows water to quickly infiltrate whenever we have a rain event. And then it flows in and fills up these rock layers underneath that are about 40% void space. And so water moves in very quickly, fills this up, and then in between storm events, it slowly infiltrates into the soils below. Now, if we don't have great soils, we can put in an underdrain to allow that water to move downstream into the stormwater system. But typically here in Florida with our well-drained soils, if we have enough separation from the water table, that water will just infiltrate into the ground below. Now, one of my favorite analogies of being able to tell the difference between these and the conventional asphalt and concrete, porous asphalt, it's really difficult to be able to see what the difference is. You really got to know what you're looking for to be able to see it. But porous concrete, the best way to understand what that looks like is it's essentially a Rice Krispie treat. And if you think about how Rice Krispie treats are made, it has a very similar structure. The difference between pervious concrete and regular concrete is that regular concrete has like aggregate or stone, cement, and fine particles. Pervious concrete doesn't have those fine particles. And so what happens is those gaps between those large aggregates that are cemented together, those gaps or voids, they get interconnected and they allow water to drain through. And that's how water is able to infiltrate there. Moving on to bioretention or rain gardens, the real difference between bioretention and rain gardens is that an engineer designs a bioretention to meet certain performance standards. A rain garden can be basically constructed by anybody in their yard on the weekend very quickly. Essentially, these are vegetated depressional areas where stormwater runoff is collected and allowed to infiltrate either into the ground or taken away with an underdrain and directed into the storm drain system. Either way, the bioretention media, the soil there and the plants help to improve the water quality, filtering out particles and pollutants as the water goes into it. Now, we typically have a depth of about 9 to 12 inches, and we don't want to go much higher or deeper than that because we want this to be able to basically drain within about 24 hours. You don't want these basically becoming ponds that maybe attract mosquitoes or anything like that. So essentially ensuring that we don't have too deep of a water and we have good conditions ensures that these will drain within that amount of time. Infiltration trenches or dry wells are another practice. You can think of these if you have a septic tank or a septic system, if you're familiar with how those work, they're not too different from essentially the drain field. We essentially route the stormwater into a long pipe and that is pervious or permeable, allows water to drain out to the sides. And there's rock around that to keep sediments from the surrounding area from migrating in and clogging. And basically that water flows into that pipe, flows laterally, fills up the stone, and then slowly drains into the soil around it. Really important that we don't have sediments coming into these because sediments can clog this. So really what we're looking at here is a lot of times roof downspouts. And if there's any type of leaves or anything, we've got a screen in there to basically keep that out of the pipes here. So it's pretty critical to have pre-treatment. Then swales are great. They provide a lot of function. They provide the conveyance or moving water from one location to the other, but they also can reduce the amount of runoff by infiltrating through the soils. And even if those soils are not very permeable, the flow through the vegetation can help with treatment of the water quality from runoff. And so you see these basically on the roadsides. You'll see them adjacent to parking lots. They typically have very low angle slopes, so they're not very steep. They're fairly shallow, easy to mow and maintain, and they do a great job with retaining sediments. Now, a more mechanical or engineered system here that I'm including are what are called nutrient separating baffle boxes. And they're not necessarily like using soil and using the natural system, but they do provide some pretty important functions in an area or in a situation that we don't really have another option to do the same thing. What these do is, number one, you have stormwater coming in, and this is usually you put this within in the middle of a stormwater pipe, right? So you have water that's coming in, and you take out that section, put in this box, and it basically allows for sediment to fall or drop out of suspension behind these different baffles at the bottom. So you see sediment all along the bottom there. And then it has a screen at the top to capture any kind of floating debris, like vegetation that can have nutrients in it, and other debris that can basically be transported downstream. And so then you open these hatches to maintain it. You take out what's on the screen, and then you suck out the sediment, and then it's ready to go again. And so it's really in a very small footprint, and it removes debris, sediment, particulates, oils, and grease, and it's pretty straightforward to maintain. Now, in thinking about sort of which options do we go with, and a lot of times when engineers are thinking about what kind of treatment do we want, we often want to think about what are the processes, or what do we want the processes to be to achieve the nutrient removal. When we think about sort of nitrogen, I talked a little bit about this before, where about half of nitrogen is in a particulate form. So that sediment, sellable, and suspended fractions here on this graph on the left, those particulates can kind of fall out. Think of that as being like leaves and other sticks and debris. There's nitrogen in there. But then there's the dissolved fraction in nitrogen that is the green here, the organic, the NH4, which is ammonia. And then we have nitrate and nitrite at the top. And so oftentimes with our GSI, we want to facilitate the right processes to remove or transform or remove the types of nitrogen or the types of pollutant that we have to effectively treat the water. And so when this is another figure from that University of Arkansas manual, there's one way to kind of think about this is that there's a range of options along a mechanical to biological kind of axes, and then there is an axis of increasing level of volume reduction, right? So we go from very mechanical on the left, where we're looking at underground detention, oversized pipe, flow control, really just looking at the volume control and how water is moving through, all the way till we start seeing more biological functions integrated into these practices. Things like vegetated roofs or green roofs, even vegetated walls, permeable pavements, rain gardens, infiltration basins, where we're starting to integrate much more of the biological functions. When we think about sort of some examples where this has been really implemented fairly successfully, I've used this example for a long time. And full disclosure, this is not in Florida, but I think it provides a really great example of where they really kind of really went back and thought about, oh, what can we actually do here with this site, and what are our options to still maintain what we have as a vision for this site, but also integrating stormwater management more effectively into the site. And so on the left, you see this is kind of a townhome development, Winterberry Road. And initially, they had essentially done the conventional approach where you have conventional pavement. The runoff went into these sort of storm drains or catch basins that were then piped from all over the site into two stormwater ponds there in the top center and the upper right. But what they did when they went back and revisited this was they started thinking about, well, all that pavement, maybe it doesn't need to be impervious. We could probably use porous pavement. And these catch basins, what if we use swales instead of stormwater pipes and tried to infiltrate this and do that, and incorporating some drainage infrastructure? And what they were able to do essentially with this redesign, we don't always think about the indirect benefits of reducing the amount of runoff. For example, one aspect is that permeable pavements, that is more expensive than conventional pavement. But if you think of it just in that context, oh, the permeable pavement's more expensive directly 1 square foot per 1 square foot compared to conventional pavement, not really seeing the big picture. By redesigning this and accounting for the reduced imperviousness, they were able to reduce the 1,600 feet of curbing, eliminate 785 feet of storm pipe, remove 8 catch basins. They didn't have to construct and buy the land and grade those 2 detention basins. They eliminated 2 outlet control structures, and they eliminated 1.3 acres of land clearing. So on a $4.4 million project, may not seem like much, but they got a lot more function out of this and saved $50,000 on the overall project. So some things to kind of think about with the summary here. Number one, when we think about LID and GSI, getting that implemented into a site really starts at the beginning. We've got to think about the site layout. How do we avoid and minimize that stormwater runoff that's going to be generated? How can we disconnect the impervious cover? Are there ways that we can eliminate curbs and gutters? In many communities, there's a requirement for curb and gutters, which essentially prevents the use of swales. So you're basically forcing the roadways to be directly connected into the stormwater system. There's some benefits to that, but it's not necessarily a one-size-fits-all in all cases, particularly in smaller neighborhood developments. And then using a compact design to reduce the footprint and area of disturbance. And then finally, really thinking about how do we make the project fit the site? How can we modify the project and make the project flexible so that it fits what the site offers rather than the opposite there? I want to go over a few resources if you're interested in this and want to learn more. First, we've got a video series that myself and Dr. Mark Clark put together. There should be a link in the chat that I think Carrie's going to put there. We go in depth on these different types of green stormwater infrastructure and some of the LID practices, really talking about it in a very simple, down-to-earth, easy to understand way. We developed a manual for Southeast Florida, looking at low-impact development and green infrastructure. That's also available. We tried to make that pretty accessible to the technical audience, but also the non-technical audience as well. And if you want to see examples of different types of green stormwater infrastructure that has been implemented around the state, we worked with the Nature Conservancy to develop the GSI photo library. And I apologize, the link at the bottom here is not correct. Carrie's going to put the correct link in the chat. But if you go there, you'll see that there are different examples of really great installations of LID and GSI from around the state. And it has a lot of information about those sites. And so if you wanted to, you could go and visit it and see it for yourself. So we have a training program if anyone is interested in becoming certified or qualified to inspect stormwater systems. This is really started out as being able to train landscape professionals to be able to provide additional services, but it's kind of for anyone who's interested and wants to be able to provide that. It's an online self-paced program, costs $100, has 10 modules, and really kind of goes over everything from the fundamentals of stormwater runoff all the way up to how do you perform an inspection and so forth. It's certification for 5 years, and you have your name in a searchable directory. If you're a licensed professional, it also counts towards CEUs and PDHs. And so the site you can see here, I think Carrie's probably going to put that link into the chat as well too. Some other sources that we also have for doing inspections are some checklists. So these are really good for kind of guiding you through that process. How do we evaluate and determine if maintenance is needed on these different types of practices? This kind of shows the inspection checklist for bioretention. And with each of these, one of the things we have is a whole gallery of photos for different types of issues that you can easily link to and see those. I want to plug or just mention FDEP has a great green stormwater infrastructure website with lots of resources, and some of the things that we produced are there as well. One of the things that we've worked on is a code audit tool for local governments. This is actually based on something that Wisconsin Sea Grant did, and something that Center for Watershed Protection also has a similar tool. But we've worked with close to 10 communities around Florida to kind of audit their codes to identify codes that either restrict or prohibit use of LID or green stormwater infrastructure. And this is something where we've seen some progress. For example, I believe it's Volusia County that went through the process, updated their codes, and now they have some incentives where developers are actually using these incentives, using the LID GSI practices, and integrating them into their development within the county. So we're excited to see that basically translating into implementation. And that process essentially goes through, developing a core team, planning, and kind of really understanding what the issues and goals are for the community. And then there's a spreadsheet tool that kind of walks you through each of these questions. And then the audit, once it's done, kind of identifies those areas where maybe communities need to look at revising or updating their codes to enable or help better stormwater management be implemented in their communities. So I think there's a link there too. And so at this point, I will turn it back over to Holly to close us out.
Yeah, thanks so much, Evan. And I think we had maybe one question in the chat, but if other people have questions, please do put them in the chat. We'll have a couple minutes for Evan to answer those. So this program is the Resilient Together program kind of came out of the Climate Smart Floridians program that we've offered in the past. So if you are interested in this program or that Climate Smart Floridians program being offered within your community, please take out your phone and take a picture of that QR code on the left. And a lot of the information that Evan has provided today, or even in our past webinars and in our couple ones coming up, if you have any questions about what's happening within your county, finding your local extension office and reaching out to them and asking them some of your questions. That's what we're here for. We're here to help you and help answer questions and trying to get the right resources, or the resources that you need for resilient work in your community. If you do next slide, Evan, please.
Yep, sorry. Let's read through the questions.
Yeah. Okay. And then, yeah, of course. So Evan, his contact information is here. So if you have any questions about anything he went over today, or if you are watching this in the recording and have any questions, Evan is really great to work with and super knowledgeable. And like he said, he's been I think you said you were a nerd and maybe your family isn't always interested in your work. I'm very interested. I'm sure everyone on this call is. So we'd be happy to talk with you at any time.
Love doing it. Love doing
So does anyone have any questions for Evan?
So Evan, I'll direct you to the one from Melissa. It was our
it. Yeah.
primary one about. Did you read that, or you want me to read it
Yeah,
out
I
loud?
was kind of I was skimming it as Holly
Okay.
was reading, kind of talking through that following slide. Yeah, this is always it's just is unfortunately a more common than it should be, where you have existing development and then adjacent area gets developed, and instead of it having no impacts on adjacent areas, you have in many cases when this does happen, you have fill that's brought in, and that area that had been undeveloped for a while likely was relieving some of that stormwater pressure, that flooding pressure from the existing development. And when you basically take that away or basically prevent water from going onto the area, it then um, backs up that water. And in worst case scenarios, you can have development around basically become kind of a berm around it where you don't have anywhere for that water to go. Now, the place to you're right on as far as being involved in the initial discussions. Um, I'd have to go back and look at exactly the process, but there is a public review of developments, particularly when there's a land use change or there's an approval of development. There has to be a public hearing on that. Um, Anytime that you're in that scenario and you're concerned about this, because at that phase, it may be a conceptual design that doesn't necessarily show what those elevations and fills would be. But I think those are the exact questions you want to ask. How is the city or how is the review process going to ensure that the fill material is not going to prevent the overland flow or the any water that is not taken by the storm system? How is it going to affect the flow of that water from the existing development? So if it blocks it and prevents it from leaving the developed area, because there's always a limited capacity that our stormwater system can handle. When we get 20 inches in a day, nothing is designed for that, right? What happens to that water? That water still needs to move off of those areas so those homes aren't flooded. And so it's really important to ask to make sure that the reviewers, the plan reviewers, are checking for that or ensuring that that is a case. And if there's any existing history of flooding that you can provide to the commissioners or the committee, and to show that there is a history of sort of some if not I'm trying to think of a way to phrase it, where it's like, hey, we didn't get our homes flooded, but the water got up really high, and it shouldn't have gotten up that high for this smaller size storm event. So when you put in this development, is it going to contribute additional runoff or prevent these larger rain events when we do have additional runoff from leaving? Because those are two different problems, actually, right? You want to make sure that that new area is not draining onto your property, and it's also not preventing water from leaving your neighborhood or your area. And so asking about how much fill is going on, how high is it going to elevate? How are you going to ensure that when their stormwater system overflows, it does not impact yours? Those are kind of the main questions that I would ask, and really ask for what is the process? How are you going to ensure this? Really pressing on those questions.
Are there specific tests or something else that can be asked for as part of the approval process? So in our particular
Mm-hmm.
situation, we're right on the water, right? We're a little
Okay.
neighborhood on canals, and
Okay.
this is directly behind us. So
Okay.
there's US 19, then there's this area to be developed, and then there's the neighborhood, and then there's the water. And so they were like, or whatever, 11. So you got to go up 11 feet to not be,
Mhm.
for any new building, it has to go up 11 feet. So for a house, that means you have to put it up on stilts 11 feet. But they've allowed this commercial development to, instead of putting it up 11 feet on stilts, to put in 11 feet of dirt.
Mm-hmm.
right? And
So
so
they
that's
should be
completely different.
required to do, yeah, so they should have to do a flood analysis if they are filling in the floodplain. If they're so here's the thing. It sounds like, and I'm kind of speculating here, but it sounds like your neighborhood is either right on the edge or maybe in what is considered the 100-year floodplain or
Oh no,
500-year
we're in
floodplain.
the floodplain. We're at like
Right,
11, we got
right,
to go up 11 feet, whatever that's
right,
called.
right, exactly. And so what I'm saying is, if anybody's doing construction and filling in the floodplain, then there has to be an analysis of that done to look at what those impacts will be to the surrounding area. And
Okay.
so the floodplain analysis, and I'd have to dig into it a little bit more about the specifics of how, okay, what if it does show that it's elevating the flood elevation in adjacent areas? There's a whole process there. They have to kind of show how they're mitigating that or preventing that in some way. That's usually, I'm kind of speculating a little bit on how that process works, but that's my understanding of how when they do when the design shows that it's impacting that, they can't just go forward with that. They have to somehow mitigate those impacts so that it's not affecting those adjacent properties.
Thank you.
Yep.
Yeah, great question, Melissa. And I think one probably we all have at some point, even if it's not near us, but somewhere else in our community. So I'm going to quickly launch our poll just so you guys, before you leave, have a chance to answer these questions for us. It is really helpful for us to just kind of know how the feel of how you guys are feeling of our topics. And then, when we do this again, what we can do better. But if there's any other questions, please put them in the chat, or if you want to unmute and ask Evan.
Yes, please feel free to reach out if you have questions.
Yeah, and we really appreciate everyone joining today and for all the sessions in the past. And we have a couple more sessions to go. So next week we'll be talking about environmental resilience. And then we also have our last week will be sort of a open Q&A. So we've, gathered questions either when you registered or from past webinars, and we're gonna hopefully kind of come together and answer those in our webinar in 2 weeks from now. We did have one question, Evan, if you have another minute. It's all projects are different. What is a typical design phase time frame? Like years, months?
Well, larger and more complex it is, the longer it's going to be. Small, a couple acre development might be like, you think about like a townhome development. That could be something as small as short as like a year. If they've got funding and they've got the resources to be able to build right away, and it's really just going through the design and the permitting, that could go very quickly. So usually, I believe, and again, I'd have to look back at the timetables, but I think it's somewhere between permitting usually takes 3 to 6 months, assuming everything goes smoothly. Now, if it's a large scale development that has multiple phases, that's going to extend, multiple years because the overall construction is going to take a longer period, and the overall site assessment and evaluation is going to take a longer period too.
Great. Thanks, Evan. Well, it is just past 12 o'clock, so thank you all for joining today. And we look forward to seeing you in next week's session. Thank you, Evan, for joining us today. We really appreciate it.
Absolutely. I'll stay on for a minute too.